Welcome to the Picture Language Seminar. It's a great pleasure today to have Professor Yitang Zhang. He is at the University of California, Santa Barbara, and previously, before 2015, he was at the University of New Hampshire. In 2013, Professor Zhang made a great breakthrough on the problem of gapped primes, showing there are infinitely many with a sufficiently large gap. And the next year, he was given a MacArthur Fellowship. And for this old work, he became well known in the mathematics community. And now he's been working on a different problem in number theory, which has aroused a great deal of interest. And he's going to tell us today about the status of that question. So Professor Zhang will talk about non-positive sequences in analytic number theory and the Landau-Siegel zero. We're very pleased to have you talk and look forward to your talking.
We say the so-called non-positive sequence in analytic number theory. So we say AN is a sequence. Everything is a real number. And a lot of problems in analytic number theory can be reduced to show some certain sequence is not all positive. So for example, we left rho n to be the characteristic function of primes. It is 1 or 0 if n is a prime. If n is not a prime, it is 0. So we can define various examples like this. So this one is let A1n to be equal to 1 minus rho n minus rho n plus 2. So just like this one, so we find that if this, so the twin prime conjecture is equivalent to one statement like this. Infinitely many A1n is negative. Yeah, A1 of n is negative if and only if both n and n plus 2 are prime numbers. In that case, it is equal to -1. So like this. And till now, we are unable to prove this. But the second one, it is in practice, it is more useful. That is, we fixed a finite sequence that is for the first one, we may start from 0. Like this. And then we let A2n equal to 1 minus rho of n plus n1 minus rho minus da da da, eventually minus rho of n plus nk. In such a situation, then when then we say A2 is negative, that could be negative if and only if at least 2 of n plus 1 until n plus nk are primes. So we can use this to describe a weak form of the a weak form of the kind of twin prime conjecture. So if there exists such a sequence, such that infinitely many A2n is less than 0, then this implies it is what we have known the result. It is the so-called bounded gaps between primes. Now the question, so, and also we can say the example 3. That we say n is an even number, which is at least is 4 or something like this. We just consider a sequence, a finite sequence. This is the one. Then this is a finite sequence. Then the Goldbach conjecture if and if A3n is negative for some n in this interval. So we have a lot of problems that could be reduced to construct a sequence, finite or infinite. Then we have 2 possible questions. One is if it is a finite sequence, depending on some parameter, capital even number n, we need to proof for all capital N, this sequence contains a negative term, just contains one, at least one. And another question, like the twin prime conjecture, like something like this, is reduced to show we can construct a infinite sequence and to show that among the terms of this infinite sequence, infinitely many terms are negative. That's our question. Now we would like to see how can we handle this problem and transfer it to the in practice it really works. We can do it. So So the question is to prove some of maybe infinitely many in practice, we do something like this. Find a sequence Pn that should be, we have the non-active condition. And evaluate the sum I say this is one, formula one. This one, and here the sigma, usually if An is a finite sequence, that's a very natural, the sigma is over is a finite sum. And usually sigma, if An is infinite sequence, it could be something like this, x is less than, and something like this. Anyway, and x is a larger parameter. So we just evaluate this. If the sum, when we can evaluate it, show that it is negative, then it is done. Then it is done, just means because this is non-negative, so the sum is negative, it is done. Actually, for the twin prime, Yang just a second. Just a second. Then we can done. So this is a very technical problem, but it works for many questions, in particular for the weak form of the twin prime questions. Then how to choose a non-negative sequence? So of course, usually it's difficult, although we just choose it, although we only have a non-negative condition required for the B of n, but in practice, it is a very difficult question. And in history, In the early history of the Siu method, was something like this. There were some interesting story about that. First, it was more than 100 years ago. It was discussed by the Norway mathematician Braun. He used some combination of the Mobius function with certain constraints to define the B of n, and it works. He got something. But later on, another Norway mathematician, Selberg, did a good idea. Did something like this. He has said we choose a real sequence Cn, which we don't have another constraint. Only thing it is just real. And let it be n to be the square of Cn. Of course, the square of a real number is non-negative. So everything is satisfied. So one becomes sigma an. Here it is Cn squared. We need to prove this is negative. So I just repeat it in such a way. Example 1. This is the twin prime conjecture. It is equivalent to this sequence contains infinitely many negative terms. Example 2, we just mentioned it. If the sequence in this way contains infinitely many negative terms, then there are infinitely many pairs of the primes PQ, such that Q minus P is Q is not equal to P, but Q minus P is less than this certain value and K. And this was first proved true for a sequence with this upper bound nk is less than 7 times 10 raised to 7. Such a numerical constant has been shaped into, right now it is 246. In practice, this is a very successful example of the so-called non-positive whole sequence in analytic number theory. And as I just mentioned it, the next time is example 3. That's a Goldbach conjecture. It's like this. So the above examples can be classified into 2 types. Type 1, like the Goldbach conjecture, we need to prove that a finite sequence contains at least 1 negative term. The type 2, we need to prove that an infinite sequence AN contains infinitely many negative terms. And so this is what I said earlier. There is an efficient method in analytic number theory to handle the type 2 problems that can be described as follows. We construct a non-negative sequence Bn, then we evaluate the sum. Where the summation sigma is taken over an interval, in practice, we often choose sigma is the n is from x to 2x, with x tending to infinity. So this, as I mentioned, if we can find appropriate coefficients Bn and show that the sum 2 is negative, then there is an in such an interval such that An is less than 0 as we need. That's enough. But how to prove the sum is negative? In practice, that's a language in analytic number theory. When the sum is evaluated, we will get an approximate expression for this sum. Then that usually contains two terms. One is the main term, another is the error term. Error term, the order of the error term is smaller, so we may ignore it. But now we require that the coefficient of the main term in the resulting expression is negative. Then in the argument, the constraint Bn is non-negative, but in practice, it is very difficult to handle how to do the Bn. Then based on the idea of Selberg's, that's called the numbered square sieve method. We can first choose this sequence Cn of real numbers, and then take Bn equal to Cn squared. That's a problem is reduced to verify that this sum is the same, is negative. The choice of Cn may depend on the parameter x, which usually is a large value. And also, we may ask, can we do this way in some alternating method to prove the sequence is non-negative? Actually, equivalently, we may think about the Cauchy-Schwarz inequalities, that if we can prove, we know that if the original question, the A of n are non-negative, then this should be less than or equal to, the left should be less than or equal to the right side by Cauchy-Schwarz. So if we can switch it, we find that this one, when we take square, then also we can prove what we need. So the above method is successfully applied to the weak form of the twin prime conjecture. However, there might be certain ways to relax the constraints. So, and get sharp estimates. We may ask, the first one, can we start with a more general form of Bn other than the form 3? That is, we do not first choose the Cn. We may have some different ways to choose the Bn, but it is also non-negative. And the second question is, can we further replace the constraint Bn greater than or equal to 0 by someone else? That's more difficult depending on the question itself. So now let's see, we may just say sometimes we may get a more general form for the Bn. Now we consider a general situation. We are given 4 sequences, C1, C2, D1, D2. So always we have a identity. We have identity just like this C1, D1 plus C2, D2 could be written as in this way. That's trivial. Then if we take the absolute value and we do it on both sides, we can get an inequality. It is also elementary. Then assume that An is non-negative. we need to get some contradiction. Then assume this kind of constraint, then the next, we are given a inequality. This is the formula 5. And on assuming for an upper bound for the right side of 5 can be the right one can be obtained, because here we have a product of two absolute values. So if we translate using the Cauchy-Schwarz inequality, so we can get the upper bounds for the right side of 5 via the Cauchy-Schwarz. So if 5 fails to hold for some choice C1, C2, D1, D2, then a contradiction can be derived. In other words, we can say the formula 4 is not always true. This is what we need. And the next, I would like to say my recent research find that in some sieve problems, also we can give them the different expressions for the weak form of the twin prime or something else. Then we will find our original choice of Cn, or we say Bn or something, could be the combination of two terms. It could be take the C1 plus C2, or D1 plus or minus D2, something like this. Then for a single C1 or C2, if we take the square, the sum is very positive, very large, well, useless. But if we take in such a form, although we are unable to directly prove these sums are negative, but the result is very close to 0. In other words, the coefficient of the main term in the resulting expression is almost equal to 0. But the left-hand side of 5 is not. This is not very close to 0. So in that case, also we can get what we need. That is, the AN is not always non-negative. And actually, this method is equivalent to showing that. Let's come back to the sum 2. To showing that this sum is negative with the Bn, it is also obviously non-negative, but the sum is negative with Bn choosing this one. That's equivalent. And here we cannot discuss the situation if we relax the condition that the Bn is negative. For some Bn, it is allowed to be negative something. We do not discuss it. Then we come to our next topic, the so-called Landau-Siegel 0. The statement of this question is, we can do it briefly. Let chi be a real primitive character to the modulo D. Then it is conjecture, of course, the generalized Riemann hypothesis for the L function LS chi said that all non-trivial zeros of this function has a real part, 1/2. That's a very strong one. But we can consider something weak, something that seems much weaker, but in practice is very useful. We conjecture that this L function, LS chi, has no real zero, which is very close to 1. How close to 1? That depends on the modulus D. I'm not going to write down the expression. Such a zero, if it exists, is called the Landau-Siegel zero of LS chi. In our approach to this problem, that is a very indirect way. We first introduce a set that's a psi 1 of primitive characters, the psi 1 of primitive characters. And we studied the distribution of the zero of the LS psi, not chi. That's a different one. With psi in the set psi 1 in a given certain region omega, capital N omega. It can be shown by discussing the gaps between the zeros of the L function, LS psi. For every psi in capital psi 1 and for every zero row of this function in omega, we have a non-negative result like this. C star row of psi is non-negative, where the precise expression for C star is difficult to write down it. But I just mentioned it is approximately equal to, for certain quantities, which are just small parameters, beta 1, beta 2, beta 3, it is approximately equal to something like this. Here, the C factor is just like the gamma factor appearing in the functional equation of the L functions. But here, this is a little different, like this. Actually, according to our definition of the set psi 1 and the omega, this inequality 6 is unconditionally non-negative. But so we say it is always non-negative, even we do not assume the existence of the Landau-Siegel zero. It is also non-negative. Then everything should be nonsense. We do not need to do something more. But here, the next, we say in our definition, this set is formally defined without assuming the existence of the Landau-Siegel zero. One is even unable to determine whether this set of characters is empty or not. So in the general, unconditionally, we can do nothing about the evaluation of the following forms, something like this. Only we have, under the assumption that the Riemann-Siegel zero exists, we can evaluate it. Then also we wish to derive a contradiction from the results on these sums like this. So I say this sum always psi belongs to the set capital psi 1, no problem. But the row runs through the zeros of LS psi in omega. We always like this. And also for technical reason, and lots of technical reason, we introduce a positive smooth wet omega of rho here. That never change. So of course, if we can, so we just say that with the aim of deducing a contradiction. So if we can prove that the sum 7 is negative for some BS psi, then also a contradiction. But just like the previous problems in sieve methods, we are unable to do this directly. We argue with the relation similar to Formula 5. We just use similar to this one, then we can find some contradiction. Then also we construct several functions B, J1, J2 on my paper. They are just a finite sum, just like it's called the Dirichlet polynomials like this. All these are just the finite sums. Then also let CS chi psi similar to CS psi is the gamma factor like this. So we assume these conditions. We have this relation like this. It is a little complicated. But now let's take the absolute value on both sides. We get a relation like this. Then we evaluate the sums like this. We plug into the double sum with the factor C star and with the positive weight omega. We get this one. Then using this one also we can see from the functional equation for the L functions, we can find that in our sum, this part is very close to 0 on average. And also our choice of the capital B as psi shows that this is also very close to 0. And also we can evaluate the left-hand side. Then our result, I say this can lead to a contradiction if these functions are appropriately chosen. We will find that the left side in absolute value is larger than the right side. Then it is a contradiction. The contradiction just means these sums cannot be evaluated in such a way. But that follows by the assumption that the Landau-Siegel zero exists. So in other words, the Landau-Siegel zero cannot exist. That could give just a partial result toward this conjecture, like this. So let me say again, I apologize for what happened to the earlier. I couldn't find the PPT, but now it works. But here, let me say something just earlier. It is just in the analytic number theory, in particular about the sieve methods concerning the prime numbers like this. A lot of questions could be regarded that let's construct a sequence satisfying these conditions. But until now, what I like to say is, for most questions, we do not have the optimal choices of the sequences. Something is just like the experiments. We try several cases, we try several types, or then we can get the result. So in this direction, many things can be done. And also another one is to evaluate the sums like the formula, like the sum 2, or maybe in general, if we take the Pn in such a form. There's also the restrictions on the length of the sums. If the length is too long, then a major problem is that we are unable to handle, we are unable to handle the error terms because the error terms could be larger than the main terms. In that case, we can do nothing about that. So also we have lots of questions. But, and also I say this inequality is just similar, is equivalent to our choice of the B1 equal to the square of C1. But something new is in our argument is we introduce several parameters and we use this one. Actually, the right-hand side, still we have to use Cauchy-Schwarz to find the upper bound. But Cauchy-Schwarz applies here is the AN should be non-negative, otherwise we can do nothing. So where it is involved something more complicated in the argument. And about the Landau-Siegel zero, I have a new version on the way to prepare, and hopefully we can really get something. And the precise definition of these involves functions. Sorry, it's so complicated and it depends on a lot of things. So it is very technical. So let me just start here. And do you have any questions or something like this?
Thank you very much for a wonderful explanation of your method. It's very interesting, and I'm sure there will be a great deal of discussion. Now, I wonder, you had such a beautiful explanation, and you said your new paper is forthcoming. But at this point, do you have any theorem that you can tell us about?
Okay, let me write down on the board. Can you see me?
Yes.
Okay. Actually, the no. We say no Landau-Siegel. What happened to is equivalent to a inequality for the lower bound. I say depending on the modular D. Here C is absolutely constant, so like this. But we may prove I say it is K. Here K is also a constant. In my previous version, I give the K is like that was last year. it is there's a K. Like this. And this result, this result, of course, we can further shift this value. Actually, it is possible to find some K value, which is negative K, is less than 1,000, it is possible. But we are unable to reach this result. But this should be a good result. And also what I can mention is, my previous version was so complicated. We can simplify the argument a lot. And also that contains some, although that's a minor numerical errors, but still we have a lot of things to improve everything. So like this, that's the result, what I can say.
Thank you very much. So I think we should have a gallery and allow questions from the people in the audience. When you talk, please turn on your video so we can see you from face to face. Are there questions from people who are attending the talk?
Yes.
Hello.
Hello?
Okay. So I was interested about like the sequence AN you mentioned at the beginning, where you said that like the sequence that can like summarize the number theoretic aspect of the problem. For example, like you can construct a sequence to study the Goldbach's conjecture, the twin primes problem, and the prime gap. So I learned that in Goldbach's problem, there's like a modification of the sequence from the original one. Like when the mathematicians, they develop like different weights, like Richard's weights or Kuhn's weights, or like Chen Jingrun's switching principle. So I'm curious, like if there's like a modification of AN in the problem of prime gap, because currently I only see that like from Golson, Pins, and Urim, from the work of yours and from the work of Maynard, they didn't really modify the shape of AN. So I'm wondering like if there's like a direction for that. Thanks a lot.
Okay. So I would like to mention one thing about the Chen Jingrun's. That has something to do with this. It is the main things. It is that also has something to do with what I introduced earlier. But the crucial step in Chen's argument is like this. To estimate the number of P is a prime, such that the N is a large even number, N minus P. To find the upper bound. So this is, but using even directly using the Pompeo-Rabbinic Gratov theorem, yeah, we are able to find the upper bound, but it's not sharp enough for our purpose. For Chen Jingrun's 1+2, the result. Then it is transferred to this one. P1, P2, P3, they are all primes. And they are we have certain constraints like this. They are just inserting. I'm not going to say. Of course, the number of the set. Originally, people consider the set is n minus pp less than n. Now transfer to this set. The number of these two sets, among this set, how many terms is of P1, P2, P3? That's the same. Among that set, how many terms is the prime? That's the same. So Chen transferred to this one. Then the Chen's argument is that's also find that's the Selberg. These are real number, and the number P equal to 1. Something like this. That comes from Selberg's theory. That I call it the number the square method like this. So Chen's argument is to estimate this is the sum. This is the Chen's crucial point. Transfer the estimate on this set to that set. These are the trivial equivalent, but he estimated something like this. Remember the n, the coefficients, because here it is real, so it is everything is non-active. But if this is the prime, it is equal to 1. So we just need to find this one. That's a so-called sieve method, the Selberg's sieve. As I mentioned, similar to what we did earlier. But the technical details are quite different. Okay.
So are there other questions? Oh, you want to follow up, Blue?
Actually, like my main question is about like, are there like any modification of the like the weight an like for the problem for like prime gap? I'm just curious because I learned that all the like the present papers they continue to use the same an like for prime gap.
Yeah, in our question, the an, let's see, in the twin prime situation, an may not be changed to replace by something else. It's not like this. But in the Goldbach conjecture, also in some weak result of some other prime problems, this transition should be very useful. That's for the an, not for choice of bn, right?
Yeah. Thank you.
No problem.
So are there other questions?
Does it yeah, that doesn't mind if I ask another one?
Go ahead.
No problem.
Okay. Actually, like the original question, I was like more focused on like the bounded gap between primes. I'm like curious about the an in that problem because I learned that it's I learned that it's like 1 minus a summation over some characteristic function of prime numbers. I learned that that's the current ways that is chosen to study this problem, and they also use this form of an to obtain the 246 upper bound. So I'm wondering, like, is it possible to just modify the shape of an in the problem of bounded gap between primes to like obtain some improvements?
Yeah, because there are various sequences, as I mentioned, the n1, n2 to nk, but which is a fixed finite sequence, right? There are many choices like this. Of course, there's a certain way. There should be some certain way to
modify this, the choice of A, and maybe even, for example, you may put some weight for this. I say AN original is 1 minus this one. But if you like, depending on the question, here you may put some C1, CK, or something. In some special case questions, maybe put these kind, putting these coefficients here, the weight something helps to find something new. I have been thinking about some possibilities like this, but till now I don't have the certain results in this direction in hand. Okay.
Thank you so much.
This is a generalization, depending on the question itself.
Thank you, thank you. I see there are many experts here. Are there any other questions from people in the audience? Well, if there are no other questions, I want to thank you again for giving an absolutely beautiful talk. And we look forward very much to your future results and to your upcoming paper, and wish you the very best. Thank you. Thank you.
Okay, thank you so much. I apologize for the PPT trouble earlier.
Oh, there's no need to apologize. We've really enjoyed your talk very much. Thank you.
Thank you.
Bye-bye.